The equation x cubed minus 300x equals 3000 has how many solutions? No real solutions, one real solution, two real solutions, three real solutions, or maybe infinitely many real solutions. So if you take one quick look at this equation, you can see it is a cubic equation. It involves x cubed as well as some x term as well as a constant. And now you might be tempted to try and rearrange this to make it equal 0 and then try and solve it like you might try and solve a typical quadratic equation. But I certainly wouldn't recommend that approach here because, well, number one, you probably can't remember the cubic equation, even though there is one. And number two, they don't expect you to do that as part of the Oxford Maths Aptitude Test. We need to do this qualitatively, not quantitatively. We don't need to solve for any particular value of x, but we do need to recognize how many solutions this equation has. And a good way to do that is purely a purely graphical argument. And when I say graphical argument, I mean take the left-hand side and plot it as a function of x, and likewise take the right-hand side and plot it as a function of x. If you can somehow plot those two functions of x on the same graph, if those functions intersect on the same graph, then you know there's going to be solutions between the left-hand side and the right side being equal to each other. And that's the approach I'm going to take here. So let's start with the left-hand side. The left-hand side is a cubic function. It's the x cubed minus the 300x. And if you know a thing or two about cubics, you'll know they all kind of look a bit like an S shape. So all positive cubics look a bit like this, right? When I say a positive cubic, I mean the coefficient in front of the x cubed is positive, and it's that number there, the positive or negativeness of that, which determines whether you have a kind of positive S shape or maybe a negative S shape, right? So any cubic where the coefficient of x cubed is negative, it might look a bit like this. Moreover, there's a few other subtleties to consider here in that how many turning points we have. Here I've drawn the cubics with 2 turning points, but some cubics, they just have 1 turning point, and indeed some cubics, they just have 0 turning points. So here's 1 turning point. That's looking a bit like that. That's just 1 turning point right there, perhaps. And also you get cubics which involve 0 turning points, and they look a bit like this. And these are all examples of positive cubics. That's where the coefficient of the x cubed is positive. It is worth noting, perhaps, whilst we're here, that in all of these cubics, you get a point of inflection. That's the point where the gradient stops decreasing and starts increasing. You can see as you go across here, the gradient is positive, positive, and then it's negative. So the gradient is always decreasing. And then at some point here, it actually stops decreasing and starts increasing again. That's called a point of inflection. On this cubic, that point, the turning point, is the point of inflection. And on this cubic, it must happen around about there. So you can see how we're going gradient decreasing, decreasing, and then it starts increasing again. That's where you start bending away as opposed to bending towards. So that's called the point of inflection. All of these features are common to cubics, but as I've said, some cubics have 2 turning points as opposed to 1. The number of turning points is ultimately determined from the gradient function itself. So, you know, you could write a general cubic out, ax cubed plus bx squared plus c and then x and then plus the d and set it equal to 0 perhaps, or maybe just set it equal to y if that was some function, the general cubic function, and you can differentiate this and it gives us 3a, lots of the x squared, plus 2b, lots of the x, and then plus the c on the end, and that would be the gradient function itself. And it's how, if we were to try and solve that gradient function to 0, ultimately we'd be solving a quadratic to 0 because we have the x squared, the x, and the constant here. And the number of solutions that come out from the general quadratic is determined from what we often refer to as the discriminant of the general quadratic. So here's how we often write down a general quadratic equation: ax squared plus the bx and then plus the c. And if I want to set that to 0, the general solution is given by the quadratic formula, which looks a bit like this. So negative b plus minus b squared minus the 4ac. And this thing under the square root is called the discriminant because it discriminates between how many solutions we have. So this thing right here, it's the square root of, let me call it d. D is the b squared minus the 4ac. And when the d is positive, you get 2 solutions. to that quadratic being equal to 0. Why is that? Well, you get plus and minus the square root of a positive, and therefore you get the two solutions coming out in the solution to that quadratic equation equals 0. If d equals 0, you just get the one solution, and that one solution is in particular the negative b divided by 2a. So that's when the square root goes to 0, you just get negative b on 2a. And in particular, when the d is negative, you get no solution. And when I say no solutions, I mean no real solutions here. So I'm not considering complex numbers in this question. No real solutions. And the number of solutions to a quadratic equals 0 is ultimately what we're doing here. So when you differentiate a cubic, you get this equation. And if you want to set that to 0, i.e. to find the turning points on the cubic, it would involve setting that gradient to 0 and then solving that quadratic. So if that quadratic has a discriminant, which is greater than 0, we have this situation here. If that quadratic has the discriminant, which is equal to 0, we have this situation here. And if that quadratic has a discriminant, which is less than 0, then we're going to have this situation here, where that quadratic is indeed the gradient function of a cubic. Now, for this question, I can see just by looking at it, we have a situation where we have two turning points on the cubic. And I can see that because, well, when we factorize this cubic, we get x times x squared minus the 300. And we can further factorize this quadratic factor here as using the difference of two squares. So the difference of two squares looks a bit like this. A squared minus b squared is the a plus b times with the a minus b, okay? That's a particular kind of factorization process which typically comes up when you're dealing with quadratics, called the difference of two squares, because whenever you have one thing squared minus nothing squared, you can always write it as this product in particular. Turns out to be very useful. And here, the x squared is the a squared, and the 300 is the b squared. So b itself is going to be the square root of 300, and the square root of 300 is just 10 root 3. So you can write this as plus 10 root 3 here, and then minus 10 root 3, like that. And why is this useful? Well, I'm writing the cubic in a factorized form. This factor times this factor times this factor. And in particular, that the product of those three factors equals the left-hand side. And the left-hand side is therefore going to go to 0 when any one of those factors is 0. The first factor goes to 0 when x equals 0. The second factor goes to 0 when x equals negative 10 root 3. And the third factor goes to 0 when x equals the positive 10 root 3. So that tells us when that quadratic goes to 0. So let me sketch out the function on another slide here. We have a cubic doing this kind of thing. And we've just figured out where it cuts the x-axis. It cuts the x-axis at 3 points. Is x. The first point was the negative 10 root 3, that point there. The second point was just 0, and the third point was the 10 root 3. That's the 3 different roots of that cubic. The y-axis is naturally where the x value is 0. So it's right there. We have yet to find the turning points, this point here, this point here. Let's go ahead and find that now. So the cubic itself was the x cubed minus the 300x. If we find the gradient function of that, well, that just involves differentiating the left-hand side. So that's going to become 3x squared minus 300. That is itself the gradient of the left-hand side. And I want to set it to 0 because, again, at the turning points, the gradient is going to be 0. That point there, and that point there. And we can go ahead and solve for the value of x. It's not too difficult. You can factorize it or just rearrange it. Let me factorize the 3 here, and you get the x squared and then minus 100 equals 0. And then you can further factorize that x squared minus 100 is just x plus 10, x minus 10 in that fashion equals 0. And again, I'm using the difference of two squares there. And yet again, we have the product of 3 factors equals 0. So when any one of those factors goes to 0, that's when the gradient function itself, that's what this thing is, dy by dx of the right-hand side, is going to go to 0 at the turning point. So that tells us the x value here is negative 10 and also positive 10 at those turning points. So this one right here is going to be the negative 10, and this one right here is going to be the positive 10. Okay, looking good. Now, all that remains is to find the y values at those particular points, and that's going to happen, well, you just need to plug the x value of negative 10 into the right-hand side function itself, What does that leave us with? It leaves us with negative 10 and then cubed and then minus the 300 times by the negative 10. And that leaves us with negative 1000 minus 300 times negative 10, which is the same as minusing 3000, which is adding 3000, and then negative 1000 plus 3000 is going to be the 2000 here. So the y value right there is going to be 2000 right there. And the y value right here is going to be the negative 2000, like that. Okay, so all that remains is to draw. So we've drawn the left-hand side. Let's go ahead and draw the right-hand side. That's going to be this side here, right-hand side. That one there. That one is dead easy to draw because I'm just drawing the graph of y equals 3000. And when you draw the graph of y equals 3000, well, it's just going to be a horizontal line where the y value is always 3000. So it looks a bit like this on this graph, a bit like that. So that's the, should have joined up there. That's the line of y equal 3000, and it's going to cut the y-axis at 3000 itself, naturally. And every point on that line, just to be clear, the y value is equal to 3000. Okay. Now, here's how we reason qualitatively. You can see how this line of y equals 3000 is above that turning point, and therefore it doesn't intersect that kind of curvy part, that bendy part of the cubic. It only intersects the cubic right here. And for that reason, we're only going to get one solution to this particular equation, and that solution is going to be whatever the x value is right here. So the answer to this question is one real solution. But let's just expand on that point a bit further. If this 3000 was to be different, suppose it was to be equal to 2000, well, that would put us as a horizontal line. It'd be looking a bit like this down there, and you can see how it would just be passing through that turning point if it was equal to the 2000, and it would also be passing through this point over here. And actually, it's going to give us two solutions: the one right here and the one right here. So if the right-hand side was the 2000, then we would get two solutions. If the right-hand side was between the 2000 and the negative 2000, it would look a bit like this as a graph, coming down, passing through, passing through, passing through. And there we go. That's the y value equal to some number between the 2000 and the negative 2000. And you can see it's passing the cubic at 3 points. This point here, and this point here. So in that situation, we would indeed get 3 different solutions. So that's what's determining the number of solutions here. Up here, we have just one solution. Up on the turning point, we have 2 solutions. And in between the turning points, we have 3 solutions. So that's the best way to reason about that question.